look at example 11.3. We are given this brake mechanism used to reduce gun recoil consisting of a piston attached to a barrel moving in a fixed cylinder filled with oil. As the barrel recoils with initial velocity, so given an initial velocity of V naught, okay, the piston moves and the oil is forced through orifices in the piston, causing the piston and cylinder to decelerate at a rate proportional to their velocity. So here's the key here. The deceleration is proportional to the velocity. Deceleration is proportional to the velocity. Acceleration is equal to some constant multiplied by the velocity. Now we can emphasize the fact that it's a deceleration, meaning it's slowing down, so we could put a negative sign here in front of kV. And we're asked to find, velocity as a function of time is the first part, then position as a function of time, and then the velocity as a function of position. Since we're given acceleration as a function of velocity, we can call the definition for acceleration in terms of velocity and time as dv dt, okay, but also the acceleration is given as a minus k times v. We see that it's a separable differential equation. The two variables are v and t, so I'm going to separate the variables. I will put the v on the left side, so dv over v must be equal to, I'm going to put the t on the right side, it becomes minus k dt. Now I can integrate both sides. Okay, I'm going to use an indefinite integral. So integral of 1 over v dv is the natural logarithm of the absolute value of v, and that should be equal to the integral with respect to time of minus k is minus k t plus some constant c. Okay, and if I want to find v in terms of time, I can sort of raise both sides to e, and e and ln becomes the absolute value of v equals, okay, e to the c multiplied by e to the minus the exponents. Of course, I know that e to the something is always positive, so I can take out the absolute value sign. I know that v is a positive quantity, so I'll just say v is equal to e to the c is actually a constant. So I'm calling that constant a multiplied by e to the minus kt. Okay, and in order to find the constant a, okay, I'm going to use my initial conditions, and my initial condition is that at the initial time, when t is equal to 0, okay, the initial velocity is equal to v naught. So if I use this initial condition, I'm going to get v of 0, which is v naught, must be equal to a e to the minus k times t equals 0, and of course e to the 0 equals 1. This gives me an equation for a equal to v naught, or my expression for v that I need is v of t is equal to v naught e to the minus kt. So that takes care of the first part, v as a function of x as a function of time. Right here I already have v as a function of time. I'm gonna use my equation saying that my v is actually dx dt. I already have the v, therefore my dx dt is equal to v naught e to the negative kt. I get a separable differential equation. I'm going to do that on the next slide, telling me that dx over dt is equal to v naught e to the minus kt. I'll separate variables. I'll keep x on the left side and the t's on the right side. It becomes v naught e to the minus kt dt. Okay, and I'll integrate both sides. Integral of dx is x, must be equal to integral on the right side will be v naught is a constant. Okay, integral of e to the minus kt, I'm going to need a little bit of u substitution here. I'm going to need a minus k here. if I let u be equal to minus kt, the du will be minus k dt. So I needed to add a minus k there. Therefore, in order not to change it, I'm going to have a minus 1 over k here. Now I can integrate v naught times, so I'm going to get a minus 1 over k here. Okay, integral of e to the u du now becomes e to the u, so it's going to be e to the minus kt c1. So I'm going to need my initial condition now. So initial condition is, let's say at t equals 0, let's take the initial position, okay, to be 0. So our x now is the distance, the position relative to where it started, so that x is equal to 0. 0 on the left side must be equal to minus b naught over k. E to the 0 is 1 plus c1, which gives me c1 is equal to v naught over k. And therefore, my x now as a function of time must be equal to, so this one here, c1 is v naught over k. So I substitute that up there, it becomes minus v naught over k, e to the minus kt plus v naught over k. To simplify this, I'm going to factor out v naught over k. The positive one here, I interchange the order. So 1 minus factoring out minus kt. This is my x as a function of time. Okay? And I think I have graphs for this. Here's the graph for my v. By the way, this is my v. It's equal to v naught e to the minus kt. So it's an exponentially decaying function. Starts at t equals 0, v is equal to v naught, and it just decays exponentially. Okay. And then my graph for x is right here. It's also an exponential decay, but it starts at 0 initially, and it approaches to an exponential decay, this asymptote of v naught over k. For the third part of the solution, we want an equation of v versus x. Okay, and there's two ways of doing that. We have here x as a function of time, and previously up here we have v as a function of time. What we can do is eliminate time in the two equations, so we end up with just an equation containing v and t. Or we can do it even more direct. We can use is our magical relationship that doesn't involve time. A is equal to d dv dx, okay, which means that the left side substituted here, d dv dx is equal to negative kv, giving me a separable differential equation separating the variables. Actually, the v's will cancel. Okay, so I'm going to have a dv is equal to minus k dx, infinite integral, right? Saying that when x equals x naught, when x naught was 0, v equals v naught. Remember, at t equals 0, we said x equals 0, but at t equals 0, v is v naught. And this is at any x here, the corresponding velocity is v. Okay, integrating the left side, integral of dv is v. v naught to v must be equal to negative k x evaluated from 0 to x, okay, giving us v minus v naught is equal to negative kx, or kx, which is just a linear relationship between the velocity and position, and the graph would be somewhere here. So it's linear function when x is 0, where it starts, velocity is v, and it just at the final position, okay, the velocity goes to 0. That's it.